Okay, welcome back to the next bit of DB2 and our discussion of tactical optimization inside MonetDB. In particular, the order indexes that we have not talked about yet. As a side remark, if you hear some strange noises during this video, then that's because there's thunderstorm going on outside. So let's see whether the equipment holds up here. Okay, so let's recall where this order index business came from. Right. We were looking at this decision tree, the tactical optimization decision tree of the algebra.select operator. And if we couldn't take these particular promising branches of using direct access in the presence of a dense but or binary search in the presence of a sorted but, then we would resort to this option of applying an order index to the but t. Order indexes can be used to establish sortedness again, and once we've established sortedness, we could use binary search. So let's quickly review how this is going to work. So here we are back in the order indexes tactic of algebra.select. Okay, so let's assume that dense and sorted are no option, but there is indeed an order index on the but t. So let's first have a look at but t. So indeed, this is an integer column, so it cannot be dense. And it is indeed not sorted. It's neither sorted nor ref sorted, so no useful ordering on the tail column values of but t here. But what we've got is another but, the representation of the order index also in but form. Okay, so indexes come in but form or an array form in MonetDB, not in the form of tree shapes as we've discussed in the last video. Okay, so that should be no surprise. And the idea behind the order index is really super simple. Once you've understood what the algebra.projection operator in MAL does, then you can immediately spot what the order index idea is. This is just a normal but, and the entries in the tail column are used to reorder the entries of but t here. Okay, so what's the semantics of this value 5 in the order index? Well, it says that the value at offset 5, that's this value, the value at offset 5 should indeed be at offset 0 in a sorted but. Okay, and that's where the algebra projection regarding OI index, the order index, and the but t will place the 38, namely in offset 0 here. That's where it belongs in a sorted but. Or again, let's see, the semantics of this 2 here indicates that the value in the original but at offset 2, this 42 value, would indeed be in offset 4 if the but would be sorted. All right, so the 42 would be put here in offset 4. So this is the semantics of the order index but, and it's also indicated in this bullet below here. So that's the super simple permutation representation, the sorted permutation of but t in a but itself. And since we are using or representing this but this order information in terms of buts, we can of course use just mul operations to apply this order information to the original input but. Once we've done that, we are left with ordered but. All right, so 38, 39, this is ascendingly ordered. But if we are looking for a particular value v here, maybe for the 42, for the 42 again, then we could just use binary search, just like we described in the last video. And this is indicated by these intervals and their pivots that I've added here on the left-hand side. We could just use binary search on this order indexed but to look for the value 42. Okay, so that's the basic idea behind order indexes. It's really super simple, and they are really very simply applied just using algebra projection. All right, so let's check whether MonetDB indeed exploits the presence of order indexes when it comes to the evaluation of algebra select. Will it indeed follow the path in the decision tree and find the order index when it promises a speedy algebra select evaluation? To do that, I will switch over to the MonetDB terminal and start MonetDB in a particular special debugging mode, which allows us to trace the decisions that are being made in that decision tree. All right, so I'm switching over to a console here, and I'm executing this particular command. So I'm using the mserver5 command to directly start the MonetDB server. I'm not using the MonetDB wrapper command in this particular case. And I'm specifying a number of parameters here, but I'm particularly specifying the --algorithms parameter, which prompts the MonetDB server to print debugging information regarding the choice, the branch taken in the decision trees of these mul operators. You will see that it indeed prints much more information, debugging information. As you can see here, I've just started the thing. The debugging information is scrolling by really rapidly. Let's see and wait for a second until it comes to a rest here. So lots of stuff during startup is going on already, and we see lots of information. I think we are done now. So the MonetDB SQL module has been loaded. All right. So I think this should be a working server now, a working MonetDB server now that is ready to host an M client shell. But when we run mul commands, we will see output regarding the decision trees here on the terminal. Let's see. So let's first start MonetDB mul session here. All right. So this session is now connected to the server, to this server here that produces debugging output. Okay. So because we want to talk about order indexes in this mul session, we will include functionality regarding order indexes into our mul session. All right, there we go. And then we will create a BUT that much looks like the BUT that we've just seen on the slide. It's an integer BUT, and it has an unordered, completely unordered tail column. It's not sorted. It's not ref sorted. It's nothing. It's unsorted. Okay, so let's check whether this is indeed the case. Scrolling from the top to the bottom to this BUT, so nothing sorted there. This is the actual state. All right, so now when we perform an algebra select on this particular BUT, it's a range select that looks for tail values that lie between 40 and 42 inclusive. All right. Then probably the system cannot do much. This is not an ascending BUT, it's not a descending BUT. There's no nice properties here. The decision tree will probably lead us just down the entire tree to the leaf, to the linear search, or as we will see, it will be the full scan leaf inside the decision tree. The worst case then can actually hit us. So let's first evaluate the algebra select here. All right, it indicates that 0, 2, and 6, the rows at offset 0 to 6 in this selection vector are the hits. In this operation. 0 is 40, 2 is 42, 6 is 41. Yeah, these are exactly the values in the requested range. Okay, so this worked just fine. Let's switch over to the terminal here and see the tail of the console output of the mserver5 server process, and we indeed see that this BUT select has indeed performed a full scan for a range query for values between a lower and an upper bound inclusive. So this is really the worst case. The bottom, the leaf of the decision tree has been hit. What we also see that the system is indeed aware of the properties that the incoming and the outgoing BUTs will have. So this is the input BUT. It's just the BUT T that we have that we had as input in our BUT select operation. And it has properties TN, which means it's a transient BUT, a malloc BUT, not saved to disk anywhere, and it's a no nil BUT. Okay, so there are no nils in the column, and the system knew about that, but otherwise no nice properties of this particular BUT. All right. The output, the selection vector of the but select, has properties tskn. Okay, so that's still a transient but t with no nil values, n. Okay, I can see that. But it's a sorted but, the system says, as sorted. So it's indeed a sorted but, 0 to 6. This is ascending sort order, all right? And it's a key but, it's a unique but. So all these entries here are unique. And that's, of course, a property of all selection vectors. A row is either included in the result or not. So there will be no duplicates here in the result. And, well, that would be a TSKN but, a transient but with no nils in sorted order and unique entries. That would be the output of this but select operation. Okay, so but regrettably and sadly we had to use a full scan to evaluate that. Okay. Okay, so now let's create an order index. Let's create an order index for but t. There hasn't been one. Now let's create an order index, which indeed comes in but form too. All right. So that's why we can access this order index and save it into just a normal mel variable by using this mel command, and then save it in a just normal but of OID columns. Okay, so let's do that. Let's create an order but order index and then retrieve it and look at it. So this would be the order index for our original t but. Let's see. The semantics of this pair is that the value that is found at offset 9 in our t but should actually be at offset 0 in a sorted column. All right, so at offset 9 we will find values 36 here, and this is indeed the smallest value. It should be at offset 0 in the sorted situation. All right, so that's okay. Let's look at this value. All right, so the value at offset 8 should indeed be the last value in the sorted column. It should be the largest value actually inside our original but. So at offset 8 we will find the 45. There's indeed no larger value here in this input, but it should be at offset 9 in a sorted situation. So that's the order index that we've now available. Okay, right. So we could now use, this is just for demonstration purposes, we could now use the order index but to just sort our original but t. We will not do, the system would normally not do that and create a materialized version of our input but t, but we can do this here for demonstration purposes. We could just use algebra projection of the order index but on our original but t, and what we get will be a sorted but. Okay, just as expected. All right, so we can indeed establish order using our order indexes. All right, and now if I now return to this algebra select command and perform a range select between values 40 and 42 onto our original but t, then I would hope that the branch in the decision tree that asks whether there is an order index for but 2 will now say yes, there is an order index. Hey, algebra select, please apply the order index tactic and save yourself from a full scan. I hope that's what we are going to see when I evaluate this here and look at the server log again. So let's evaluate this. Of course, the result is still the same. Applying optimization should not have any effect on the result. Now switch over to the terminal here. Okay, you see that there is no stuff that is checking for order indexes, and indeed the but in question has an order index. That's nice. So when we come to the but select, on our but t, then we find that its properties are indeed again t and n, transient no nil but it also has property O, and that means the order index. There's an order index present for this particular but, and this is indeed being exploited. As you can see here, the algorithm that has been chosen, the branch in the decision tree that has been taken is indeed the order index but. All right. Perfect. So order indexes are indeed exploited when they are present in the system. Well, now we have created this order index by hand. We have enforced or forced this particular order index. But in the normal MonetDB operation, we can indeed count on the system to detect when it's beneficial to create such order indexes automatically in the background. And this is, of course, the case if we pose order-sensitive queries on the tables in our system. So order-sensitive queries could be such range queries that we've just seen, where some value A has to lie between values low and high. That would be the borders of the range. But there's also other operations like obviously the order by operation. So if we have to evaluate order bys frequently in our workload, then it might really be beneficial to have an order index present in our system, because that could implement order by just in terms of algebra projection. And indeed, order can also be very helpful if we are performing group by operations. Grouping a table by a particular column A is more efficient, and it's really can be really cheap if the table A is already in A order, because then all the rows that belong into one group, according to this group operation, will already be adjacent in the table storage. So all of these order sensitive operations can trigger the system, if it decides so, to automatically create an order index for us in the background. Whether this has happened can actually be checked from the SQL interface from MonetDB. As you can see, there is this SQL query that queries the data catalog, the internal data structures of MonetDB using SQL. And I'm looking at this particular catalog table of MonetDB, this storage table, all right? And I'm looking for entries that pertain to our playground table, to our index table. All right, so please give me the details about the current storage situation for the index table. Okay, I'm looking for the column names that have been that are present in that table, and whether these columns are sorted, ref sorted, unique, or whether they have an order index. And now that we know about the but properties that we've discussed in previous video, we exactly know what the semantics of these fields in this storage table are. You see the sample output for our index table here. You see that indeed the system is aware that the A column is sorted, and we can expect the algebra.select to make use of that and actually be performed differently than a select on the non-sorted C column. This answers the question of the last video, whether algebra.select is really performing all the same things all the time, or whether it's more clever. And well, this is an indication that the system is aware of the sorted properties. You also find the ref sorted and the unique properties. The A column is the key column. Of course, it's unique, but there are no order indexes currently created for these column. Whether this can be changed, let's see in another experiment. So let's switch back to the terminal here. Let's end the mul session, okay, and instead create a SQL session. Now we are talking SQL again. All right, so we could run these commands now to re-establish the indexed table. The index table, that's our playground table in these particular chapters. I've already done that for you, so we don't have to do this here. This is the A column, the primary key A column. Okay, so it will be unique and so on. You know all these commands already. This is the index table as we know it. Okay, so now let's query MonetDB's data catalog about the current properties that it knows about for all of the column buts, the A, B, C column buts of our index table. Before I start this query, let me reduce font size a bit. 1, 2, 3, 4, 5. I hope you guys can still read the output here, because the output of this query will be rather wide. So to avoid nasty line breaks, let me... Okay, that looks okay to me. Okay, we see that there is indeed some hidden internal column that is being used to save the system, to guard the system from the insertion of duplicates in the primary key column. But let's not look at this particular column. Let's look at the 3 original columns of the index table. they have the expected types, they have the expected row count. There are actually indeed 1 million rows in this particular table. And this is the column size. This is the number of bytes that are being used to store the data inside these columns. So 1 million integers occupy 4 million bytes, all right. 1 million decimals stored in that super nifty mapping from numeric 3,2 to the 16-bit short type of MonetDB uses only 2 million bytes. So that's quite some space savings there. And we see that there's all kinds of other index structures internally that we've not talked about yet in MonetDB. There's not only order indexes, but there is, of course, support for hash tables. Currently, no hash tables assigned here. For so-called imprints, which is a very CPU cache-friendly data structure, index structure that we have not talked about yet. And there are no order indexes, but well, there's the other properties that we are expecting. Yes, okay. So now let's perform an operation on the index table, an order operation by the C column. Okay, that could trigger the system to decide. Okay, it would be really valuable if we now had an order index. If we only had an order index on the C column now, things would be better, would be more efficient on the next order by. So. And indeed, we will see that the system decides to build such an order index. It will be a persistent order index on the C column that is supposed to support operations, order sensitive operation on the C column in the future. So let's evaluate this query. You can see that these two clauses here are only being put there so that the output is manageable. We don't need to see the 1 million sorted rows here. 10 rows are enough. So let's evaluate that. All right, and there we go. All right, so indeed we see the largest C value sorted here because we had this offset clause specified. But this is really the tail of the sorted output. So the query has been performed. Now let's recheck the internal properties that MonetDB has assigned and derived for all the columns of the index table. Alrighty. Okay, so we still have information about the 3 columns. Count and column size, of course, this has not changed. Hashes and imprints, they are not there, but oh, okay, there is something, something has changed here. There is an indication that an order index, oh, let me lean to the side here. Can you see that? Yeah. Oh, there it is. No, where it is. Da. Okay, so there's indeed an order index has been created for the C column, it appears. Okay, so let's indeed check. We can check the file system where all the buts regarding a particular column are being held. And I've queried the location column from this storage table that will tell us about the directory file system location, about all the buts that are pertaining to column C. So it's in directory 07734. Let's switch to another terminal here. Okay, I'm already in the data directory of my MonetDB server. And if I look there, there's the but subdirectory. I will change into the 07734 subdirectory here. Oh no, there's no such directory. Let's have a look. Oh yeah, let's change in the 07 directory. I'm sorry about that. And then look at the files there. 734. Okay, so there are the 734 files, and they are indeed, there's the tail, the persistent tail but for the C column, and there's also an order index but that has been created. June 3rd, 1241. This is the current time. All right, so let's see, date. June 3rd, 1243. This is the current time. This is the order index that has just been created for us. Okay, so the system has decided that an order index is indeed beneficial in this particular case. Okay, there's one property of these order indexes, and that is these are really very inefficient to update. So if you have a change in the values of the index column of column C in this particular case, then maintaining such an order index is really complicated. Actually, it's it almost calls for a complete rewrite, a complete recreation of this order index information from scratch. So this is really different from the case where we were talking about B+ trees, where there was really clever algorithms that were designed to maintain such a B+ tree when the underlying table is being updated. Not so for the order indexes. There's actually no order index maintenance implemented inside MonetDB. So if we perform such an update on the C column, if we perform this SQL DDL command, for example, then this will invalidate the current order index. And since we have not issued any further order sensitive query, the current order index is declared invalid. It's going to be removed and will not help anymore while we perform queries on table indexed, unless the system decides to then create a new order index. So let's see what happens. Let's perform this update, one affected row, and then recheck the current state of the storage for our index table. And I think we should see, yes, we should see that the order index is indeed gone again. It's not available anymore. And well, it would need to be recreated if the system decides that the workload could benefit from that. I think we should also see this if we switch over to this console here and then list the directory contents again. The order index for 734 should be gone. It's indeed gone. All right, so no persistent order index anymore and no support from order indexes. Okay. So such order indexes can really be performance booster. All right, and you see we could rely on the system to create these order indexes on its own. There's also the possibility to create such order indexes inside MonetDB manually, so explicitly. If we expect that there will be query workload that can benefit from such order indexes, then well, we could decide and tell the system by performing these DDL commands in the MonetDB SQL console. All right, we could of course first create and populate our table T. We would then set that table T to read only. Okay, if we set it to read only because the order index data structure that we will create in a second is a static data structure that cannot be maintained efficiently. All right, so the system has the constraint that such order indexes can only be created by users if the underlying table is set to read only and it will not receive further updates. This might seem very restrictive, but if you look at the typical workloads that you see in relation to database systems, there's plenty of tables which remain rather static or really purely static and receive no updates at all. And well, I could enforce this with this alter table command, and then I could create this ordered index on table T on a particular column A, and it will be used in subsequent query operations. Right. This, of course, will write such a T order index file on disk, as we've just seen in the console output. All right. So much for order indexes. One variant of an index data structure that is not tree-shaped but still is able to support range queries efficiently. All right, it's a completely different story if compared to B+ trees, but that's what we're here for. All right, there's one more thing regarding index-like support in MonetDB. This is not related to order indexes, but to a different index structure, the so-called crackers. Cool name. These will be the topic of the final video in chapter 9. Please join me when I talk you through the cracker story in the next video. Bye.